Zoom recording. Okay, so good afternoon, everybody. Let's rock and roll. We have to finish the slides from the previous week. And if I remember correctly, we stopped, why isn't, we stopped at slide number 19. Okay. Yes, this is what we discussed. So we discussed what a hereditary subset is, and I hope everything is clear. Are there any questions at this stage before we push forward? Nope, nobody from the Zoom because I cannot see you, but I can hear you. If you need to ask any questions, just unmute yourself and ask a question anytime you feel like it, okay? All right, so now that we know what hereditary subsets are, let's move on to saturated subsets. And unlike with the hereditary property, which can be explained purely in terms of graphs, you see, this is what this proposition is all about. Hereditary property is simply designed in such a way that a set of vertices that we remove to obtain the subgraph must be hereditary, or otherwise it will not be a subgraph, okay? But the other property, the property of being saturated, is a bit more complicated because it cannot be explained purely in terms of graphs. So this has an explanation in terms of Levitt path algebras, in terms of graph sister algebras, and you will come to appreciate this condition very much. But at this stage, at the level of graphs, it's not motivated. It's not obvious why on earth we would bother to have such a condition. But first, let's grasp the definition. So when do we call a subset in the set of all vertices saturated? Well, we call it saturated if there does not exist a vertex outside of this set with the property that it emits finitely many and non-zero arrows, and all these finitely many arrows go to this set H, okay? So that's the property. Such vertices are called regular. So it's not the sink because it emits at least one edge. So the preimage of the source map is has at least one element, but it's a finite emitter, okay? Such vertices are called regular. So what we have to make sure of is that there does not exist a vertex outside of our set that is regular and it has the property that all its arrows shoot into the set, okay? Somehow, when you will see that later on, that vertices label projections in our sister algebra or Levitt path algebra, and these projections are generators of our algebras, that simply what you see if you take an ideal generated by projections labeled by vertices inside a set H, okay, then such an idea will necessarily include all vertices which are also not as projections, which are also not in H, but which are in the saturation. Because you see, just like with a closure, if you have, I'm sorry, let me start it again. I think I wasn't clear enough. You see, it's very much like with a closure with topology. You can say that the set is saturated if there are no such vertices outside of it, right? Just like you can say that a set is closed if no limit points outside of it. So just think about these regular vertices which shoot all the arrows inside the set as things that are limit points, as things that should be in the set. And if they are not, we should adjoin them, okay? So just like we have a closure of a set in topology, which we do by throwing in all limit points into our set, and this way we get a closed set. The same can be done here. If you have a set H which is not saturated, there are some regular vertices which shoot all their arrows into the set, then we should just adjoin this vertex, okay? So you can have saturation closure of every set. And this is important from the point of view of an ideal. If we would now take an ideal generated by projections labeled by vertices from a hereditary set, then it would automatically include all vertices which are in the saturation of H, okay? But this is already in terms of algebra. I cannot explain it in terms of graphs. That's why I say that it's more complicated. Okay, now we have to be even more fancy and take into account what happens when we have infinite emitters. So if we have a graph with the property that no vertex is an infinite emitter, we call such a graph rho finite. And then life is really much easier. But a lot of absolutely fundamental examples go out of the window. So we really want to admit infinite emitters, okay? They emit countably infinitely many, but infinitely many. And this is very crucial. So we want to bundle together some properties of an inclusion of graphs, or if you want, of what we mean by a proper subgraph, in such a way that it induces a morphism at the level of graph sister algebras, okay? And so two of these properties you already met. You see, you take, so first we have E, which is a subgraph of F in the usual sense, no other properties. So E0 is the subset of F0, E1 is the subset of F1, and the source and target maps restrict respectively to the source of target maps of the subgraph E, okay? So that's by far not enough for such an inclusion to induce a morphism of sister algebras. So first, we must look into all vertices that we throw out, okay? So it's F0 minus E0. And we know that already that this is hereditary. Why? Because E0 is a subgraph. E is a subgraph of F. So if you remember the previous slide, why doesn't it work? You see, you have this proposition. Hereditary property is equivalent to being a subgraph property, okay? So by this proposition, we already know that since E is a subgraph of F, then this difference set, F0 minus E0, must be hereditary. This is an H in the previous slide, okay? But now we also want it to be saturated, right? That's this property which I just explained. And well, then we have another condition, which is not void, not vacuum, not vacuous only in the case when you have infinite emitters, but we have to take into account. So if you have, what we want to assure is that there does not exist a vertex in E0 which emits infinitely many edges into the set E0, we must make sure that there does not exist so-called breaking vertex, okay? And the breaking vertex is a vertex which has this property that it is not a thing, so it emits at least well, actually it's an infinite emitter. It's an infinite emitter, but it emits only finitely many edges into the subset E0 of vertices in the subgraph, okay? So the situation which is not allowed is that we have a vertex which is an infinite emitter, and it emits finitely many arrows into the subgraph, into the vertices in the subgraph, and infinitely many outside, okay? So that is exactly what is not allowed, all right? Of course, it's obvious that I don't have to say infinitely many outside, because if it emits infinitely many inside, and altogether it emits infinitely many, then obviously it emits infinitely many outside, okay? So this is what we cannot allow. And actually, already at this stage, if you remember the definition of a graph sister algebra, you can see why. You see this second Kunz-Krieger condition over here? If we have a vertex V, which is a breaking vertex, okay? So I have a vertex in E0. Yeah, I have a vertex in E0, which emits infinitely many arrows in the big graph, okay? So then this condition number 2 does not hold. It's vacuous because it's only for regular vertices. This condition does not make sense for infinite emitters, okay? So when I look at my vertex in a big graph, there's no condition number 2. But now if this vertex emits only finitely many arrows into the subgraph and infinitely many outside, after I remove all these outside vertices to go to a subgraph, all of a sudden, this vertex will become a regular vertex. And the condition number 2 will hold. And this is an extra algebraic relation which wasn't there before. That's why we must not allow it, okay? And of course, I will explain all of this in detail, on the blackboard, but at least I want you to have a gist of what's going on, so that you see it's not some monkey business. It really makes sense and it's well justified, okay? So this is why we must not allow breaking vertices, which means we must not allow vertices with such a property, okay? So we assume there does not exist a breaking vertex, okay? So in other words, we can say that the inclusion is unbroken. By the way, there is a way to fix it. If you do have a breaking vertex, because you have such a graph and you want to have such a subgraph, then simply what you have to do, you have to change your recipe for generating ideal, and you have to add some extra vertices. It will not be so easy. You'll still get the morphism of graph hysteralgebras, but it will be for a different graph. This graph will not be just the graph with these vertices removed and appropriate arrows removed, okay? It's a more complicated procedure, which I don't want to get into right now. I might do it during the course in some weeks, but not right now, okay? And finally, we have a condition which is somehow very easy to understand. We are saying that, remember, this is very important to look at this label. If you take all vertices in the subgraph, and then you take pre-image under the target map, but the target map of a big graph, okay? Then we get all edges in the subgraph. If I would write here E, this would be a triviality, right? It's obvious that if I have a map from E1 to E0, then the pre-image of E0 is E1. That's trivial, okay? This is no condition. The point is here that I have a letter F, right? And E1 is a subspace of F1. So what I do, I restrict the target of, I restrict the codomain of a target map in the big graph F to the subset of vertices E0. I take the pre-image and I must obtain, of course, it includes E1, but I want to make sure that E1 also includes this pre-image. So in other words, if you want a good example, it's too complicated to use this whiteboard. So try to imagine, it's very easy to imagine. Imagine that you have a graph with two different vertices and you have two edges. One edge goes from V to W and another edge goes from V to W, okay? Then you might say, all right, why don't I do a subgraph in such a way that I don't remove any vertices, but I just remove one edge? It is a subgraph, all right. It satisfies all the definition of the subgraph. Since my set H, this different set of vertices is empty. Empty set is always saturated and hereditary. There's no problem being saturated and hereditary. There's also no problem with breaking vertices, right? Because I have just one emitter, it's a finite emitter, okay? But still, this condition number 3 fails, okay? Because I'm then taking the pre-image of my vertex W, and the pre-image with respect to this target map in F is 2 edges, right? But E1 is just 1 edge, so we don't have equality of sets. The point is that you cannot, if you have a vertex in your subgraph, then you must include in the subgraph all edges that end at this vertex, okay? That's the mental picture. You cannot go to a subgraph by just removing edges without removing the target points of these edges. So the endpoint of an arrow, if you want to remove an arrow, you must remove it together with its endpoint. And then, of course, all the arrows which enter there, okay? That's very important, as otherwise you wouldn't have the following theorem. So this is a very fundamental fact. This is well known. We just introduced slightly different terminology. For some reason, people call such an E a quotient graph. I so strongly disagree that I'm changing the terminology from textbooks, because I'm really taking a subgraph. There's no collapsing involved here, right? For me, if I have a quotient, I shrink something. I have a quotient at the level of algebras, but not at the level of graphs. I'm removing these vertices. I'm not shrinking them to one vertex. Okay, but don't be surprised when you read some literature, like say the Leavitt-Path algebra book, that this is really such E is called the quotient graph of F. Okay, but I prefer to call that admissible. But never mind. This is just terminology. What you really should bear in mind, this is your take-home message, is this theorem that if the inclusion of graphs is admissible, then the natural quotient star homomorphism is well defined. Okay, and what do I mean by the natural quotient star homomorphism? Let's go back to the definition of our graph sister algebra. Sooner or later you'll memorize it, okay, but for the time being, let me have it in front of your eyes. So remember, this is an algebra which has two sets of generators, one given by projections and one given by partial isometries, okay? Since these are the universal sister algebras, it will get explained in due course. It suffices to give our star homomorphism on generators, and then if it satisfies the relations, it extends automatically, it's continuous, and so on and so forth. Okay. So you see, what happens here is that what I'm doing, I'm now taking projections which run the whole graph, the big graph. And if my projection is labeled by a vertex, which is in a subgraph, then this map is just identity. I send this projection to this projection. And if V is outside of my subgraph, the vertex V is outside of my subgraph, I just send this projection to 0. I kill it. Okay? And the same goes for isometries. If the labeling edge is in my subgraph, it's identity. If the labeling edge is outside of the subgraph, it's 0. Okay? So I have this canonical quotient map. I have my two sets of generators, and I kill all generators that are not labeled by vertices or edges from the subgraph. That's it. This is why it's a canonical quotient. But then now, of course, the name of the game is to prove that it's well defined, that such a recipe will satisfy all these conditions. Okay? And this is why these conditions of admissibility are so complicated. Okay? But they guarantee that if we have an admissible subgraph, then this simplest possible prescription of a canonical quotient map is actually well defined. And indeed, we get a star homomorphism, which is obviously the surjection, right? Because I obviously get, if I get all generators of my algebra, I get the whole algebra. So it goes without saying, it's obvious that this is the surjection. And you can call it canonical quotient surjection, okay? Any questions thus far? Okay. So yeah, and I think we can go again back to spheres and balls. Yeah, you see, so this is my ball diagram, and that's the bounding sphere diagram, right? So this graph, which is without dashed arrows, is my subgraph, and the whole picture is my big graph. And you can see that all these properties which I've been talking about are satisfied. Let's just have a quick check that this is indeed an admissible subgraph, okay? So first, I look at this one element set, right? Because in my subgraph, I have all the edges in the graph except for this last one, okay? So this different set F0 minus E0 is just this one element set containing this vertex. Well, first thing, is it hereditary? It's obviously hereditary because it's a sinc. It doesn't emit anything, okay? So the condition is automatically satisfied that all edges emitted from this vertex and in this vertex, well, there emits no edges, so it's satisfied. Now, is it saturated? Well, so I must look at any vertex outside of this set and see if all arrows shooted from this vertex, all of them are regular, okay? So all of them are potential suspects. So I must check that if I take any of these vertices in the subgraph, it does not shoot all its arrows into this one last vertex. But it doesn't, because we have loops everywhere, okay? That's the whole point. If I would skip this loop here, right? then it wouldn't work, because then this vertex would shoot all its arrows, all its finitely many arrows into this vertex. Yeah, then this set would not be saturated. But because there is a loop, we are done. This is a saturated subset. Okay. Now, how about? Well, there are no breaking vertices because there are no infinite emitters, so we are clear here. And the last property is what I told you, is that we do not remove arrows if we do not remove their endpoints. And you see here, the only arrows which are removed are the arrows which end at the vertex, which I also remove. So this condition is satisfied. Okay, right? The only arrows which are removed are dashed arrows, but all dashed arrows end in a vertex which I remove. So the condition number 3 is satisfied. Okay, so this sphere subgraph is an admissible subgraph in the ball graph. So we have a canonical surjection, which simply is defined in such a way that I kill the projection labeled by the last vertex, and I kill all partial isometries ending in this vertex. Okay, and it is well defined by this theorem. And this is precisely a non-commutative version, a quantum version, if you will, of the property that if I have the boundary sphere included continuously in the ball, right, then of course I have a canonical surjection from all continuous functions on the ball onto all continuous functions on the sphere, simply by restriction. Yeah? Every continuous function on the ball, by being restricted to the boundary sphere, becomes a continuous function on the sphere. And because we are in nice compact Hausdorff spaces, we have a theorem, right, that any continuous function on a closed subset can be extended to a continuous function of the whole set. This is compact Hausdorff. Everything is very regular, right? When you go to some very wide spaces, when you go, I don't know, beyond regular spaces, then you might have a problem, okay? But when you're talking closed subset in compact Hausdorff spaces, you're always safe, okay? So you see that also as a surjection, right? And this is, if you want, the quantum way this property is recovered. Okay? So in topology is what I just told you of having the closed subset in a compact Hausdorff space. And in terms of subgraphs, this is admissibility property. So remember, also in topology, you have some conditions. If I would take some crazy set, for instance, not closed, then this is not true. If I take an open arc in a circle, if I take all continuous functions in an open arc, they can go to infinity. You will not have a surjection by restriction. Okay. So you must have some conditions, even in classical topology, in order to claim that the inclusion of a subset in a set will induce a C-star map the other way around. Okay. Any questions thus far? Everything clear? Okay, so it's time. So this was known stuff. This is textbook stuff. Now we go to state of the art of research. This result was just published weeks ago, that theorem, and I hope to use this and the following theorem as the landmark ending points for the course. Okay, so this is what we are driving at the end of the day. And here the situation is as follows. I take graphs F and G, but in such a way that the source and target maps agree on the intersection of F1 with G1. So they agree on the intersection set of edges. If they agree, then I can take the intersection graph is well defined, and also the union graph is well defined. Okay? It's obvious that the intersection graph is well defined, and also the union graph is well defined. There's an obvious way how to define source and target maps on the union set if you have two maps which agree on the intersection. It's so easy, I'm not going to explain it, and it will be done in the course on the blackboard. So what's the theorem now? I have these graphs F and G, and I assume that the intersection subgraph is admissible both in F and in G. right? Because by making sure that the source and target maps agree, all I have is that I have a subgraph in the most naive, simple-minded way possible. These are just subgraphs, okay? But they don't induce yet star homomorphism or sister algebras. So I assume that both of them are admissible. So this gives me these two arrows. By the previous theorem, these two arrows from sister of F to sister of F cap G, and from sister of G to sister of F cap G are well defined by the previous theorem, okay? We have it. But what we have to make one more assumption. So this is somehow not necessary when we have row finite graphs, when we don't have infinite emitters. But you also have to assume that the inclusion of F in the union F with G and inclusion of G in the union graph, that they are unbroken. Unbroken in that sense which we just explained, right? So we say that the inclusion is unbroken if its property holds. There are no breaking vertices in E0, okay? It's also obvious that I could use here E0 instead of F0. Note, because I cannot have a vertex V which shoots all its it shoots finitely many and non-zero edges into E0, because this will violate the saturation property of its difference. Okay, so here I can write E0 or F0, it doesn't matter, because anyway there is no vertex V outside of E0 which could have this property by saturation. Okay, so whatever you want. I wrote E0 because that's just more adequate. Okay. So we assume that F included in the union and G included in the union graph that they're unbroken. I have to make this assumption somehow. It doesn't follow, or at least well, this is what we can do later on. I would like to find a counterexample. I would like to find the case when, if we don't assume it, then the theorem is wrong. I haven't done it yet. Yeah. I know that if I assume it, the theorem is true. But I don't have a concrete counterexample in mind to show that if everything is satisfied but these conditions, then the theorem is false. We might have fun doing it later on. But for the time being, let's just focus on the theorem. So we assume that these inclusions in the union graph are unbroken. So under these assumptions, what we can conclude is that the inclusion of F in the union graph and the inclusion of D in the union graph, that they're both admissible. We don't assume it. This is a conclusion. So in the case when we are row finite, when we don't care about breaking vertices, note that we have a very nice picture. If the inclusion of the intersection graph in both graphs is admissible, then the inclusion of both graphs in the union graph is admissible. It follows. This is very good. This is very nice. So you don't have to assume admissibility property of the inclusion in the union set. It follows. And by the way, the opposite implication is false. Here I have a counterexample. We will study it during the course. So you might have a situation in which the inclusion of F in the union graph and of G in the union graph is admissible, but the inclusion of the intersection is not admissible in one of these graphs. But it's very nice, because when you do the pullback, first you must look at the bottom arrows. The upper arrows are canonical. These are these bottom arrows which define the pullback. Okay, so it's good to have them assumed as well defined, and it's beautiful then that it follows that these are well defined. The only additional assumption I have to throw in, I don't see how, by assuming that the inclusion of the intersection set in both F and G is unbroken, how to conclude from this that the inclusion of F and G in the union graph is unbroken. I don't see it, but I don't have a counterexample. It should be easy. Anyway, so we assume it to make sure the theorem is true. And then, so first part of the theorem tells me, aha, so these both of these inclusions are admissible. So I have this canonical star homomorphism between sister algebras, which are canonical quotient maps, which are surjective. They exist, okay? And moreover, they render the diagram a pullback diagram of sister algebras. I have to explain to you what is a pullback diagram. We'll have more about it in a week. And now, in order to the whole thing about the theorem is to prove that it's really a pullback diagram, but it has these properties. But I really have an isomorphism between this sister algebra, which is given in a concrete, explicit way, to the pullback sister algebra for these maps. Okay, but the diagram is commutative. It's obvious because remember all of them are canonical quotient maps. So seeing that it's a commutative diagram is a triviality because I'm just going by identity or by zero, so there's nothing to it. Okay, but to see that this is a pullback diagram is quite a bit of work. Okay. And there is a very nice criterion. It works in the category of abelian groups. So in particular, it works for sister algebras. And there is a nice article by Pedersen, Gert Pedersen from Copenhagen. He was a famous Danish mathematician, a top expert in sister algebras. And he wrote a gigantic paper, like 100 pages long. It's very, very long, about push-out and pullbacks for sister algebras. I strongly recommend this paper. It says that his focus was slightly different, but it's like the most important paper about pullbacks and pushouts of sister algebras. It's by Pedersen. And in this seminal paper, he included a criterion, which of course was known to category theorists. I mean, it works for abelian groups, has nothing to do with sister algebras. But if you have a commutative diagram of abelian groups given by group homomorphisms, then he listed 3 concrete conditions that guarantee, it's actually if and only if I remember correctly, there is a criteria of when such a diagram is a pullback diagram. So when we want to prove a theorem, we cite Pedersen. By the way, this is a very easy lemma. We will definitely do it as an exercise. Definitely, it will be one of exercises assigned. Yeah, this is a very, very easy lemma. I mean, easy, you have to sweat to do it. It's 1 or 2 pages long, but there are no tricks used to just check it. And with this powerful tool at hand, we just have to check that these Pedersen's conditions, criteria for having a pullback diagram, for a commutative diagram being a pullback diagram, are satisfied. And here the work starts. Because it's easy to write an abstract condition, it's more difficult to verify. Okay? But these admissibility conditions were tuned in such a way that 1 page of a proof and it works. So that's our theorem, which just was published some weeks ago. Any questions here? Nope. Okay. Now, we also have a second theorem which goes beyond inclusions of graphs. So when we were looking at this theorem, everything here was about inclusions, inclusions, and inclusions. But in real life, you often get examples which are not given by inclusions. When you do topology, you often have push-outs which are more complicated than just gluing spaces. You also do some collapsing. Remember our examples from the very beginning? You see? So here, everywhere, this is not just the union of sets. This is the genuine push-out. I do some collapsing. I squeeze the boundary circle to a point, right? So what it translates to is that these maps that define the push-out are not all injective. A map shrinking a circle to a point is definitely not injective, okay? So this means that now when I replace my topological spaces with graphs, I have to go beyond injections. I also have to collapse things in a graph. Then I really have quotient graphs, not subgraphs, okay? So our next endeavor after we handled the inclusion part, the injective push-outs, the set union push-outs, was how to handle, at least under some additional assumptions, push-outs of graphs that are given not by injections, that are given not by subgraphs, okay? So that's what this is all about. And this, of course, as you can imagine, started being far more complicated, just as this topology examples from the beginning are more complicated than, I know, gluing 2 disks over the circle to a sphere. That's much easier. and shrinking the boundary circle to a point. Okay, but first, in order to phrase the theorem, I have to show you a very important lemma. I'm very happy with this lemma because it generalizes a lemma which you can find in this book about Leavitt path algebras. And let me give you from the start the main idea, and I beg you to remember it because this will be like your beacon in the darkness. It will always remind you of what it is all about. If you go to the usual definition of what is meant by a morphism of graphs, you have this obvious, most simple-minded definition which says, aha, I have a morphism of maps, of graphs. If I have a pair of maps, mapping one maps vertices to vertices, one maps edges to edges, and they are in agreement with the source and the target maps. This is a completely, totally obvious definition, and it has been useful. And this is a definition which you can use, I don't know, which was used in Leavitt path algebra book, okay? But it doesn't do the job for us. So we made the following change. We said, okay, vertices are mapped into vertices, but edges are mapped into finite paths, not necessarily edges, okay? So that's the big deal. This is the change we made. Edges can be mapped into, say, path of length 10, not necessarily to an edge. This is exactly this kind of generalization of what we mean by a morphism was necessary to be able to construct push-outs that accommodate non-commutative deformations of these topological examples from the beginning of my course, okay? And this is where we go beyond what people were thinking about before. And if you remember the course description, I'm writing, you know, about evolving graph morphisms into Leavitt morphisms. That's still in the process of being done. I hope we can do it, but we only partially did it so far. So this is really frontier of research, if you want. Okay, and now I think here I have to use, darn, I hope I'll not mess up. I really have to use this whiteboard. So I stop sharing, right? And then go to whiteboard, right? Yeah, but now I want to use this whiteboard so that I can write on the screen. Ah, here, right? Okay, good. Share. Excellent. Thank you. Okay, so Majid Bijeli, because Oscar asked me to do it, and I like the idea, will tell you in a week what are categories, you know, full definitions. It will be done as part of our recitation classes, okay? But now I want to explain something very easy, without which you will not understand what I'm talking about in these lemma and the theorem. So basically, a category is a pair. Oh my God, my handwriting is even worse here. I have objects of a category, class of objects. So in particular, it doesn't have to be the set. As you all know from high school, the set of all sets does not exist. But you can talk about the class of sets, okay? And you have, and now this is a set. Morphism. So for every pair of objects in your category, you have the set of all morphisms from one object to another. Yeah. So the most trivial example, take the category of sets. So objects are sets. We have a class of sets, and morphisms are maps. This is the most simple category you can imagine. For every pair of sets, I can take the space, the set of all maps from one set to another set. And this is a set, okay? Of course, when I take all such pairs, it will not be a set anymore because I'm not running it over a set. No. Yes. Yeah. I apologize for my handwriting. It's all C. It's C like a category. Okay, and now you say that your category is small if the class of objects is a set. Okay, so for instance, if you take all isomorphism classes of finite dimensional vector spaces, this is a set, because isomorphism classes of vector spaces are labeled by natural numbers, by the dimension, and the set of all natural numbers is a set. Okay, so if you take, say, the category of isomorphism classes of finite dimensional vector spaces, it is a small category. So you say that the category is small if its class of objects is a set. Okay, and I just gave you an example. Now, I also have a category D. And what do I mean by a functor? So Majid will do it one more time with more examples and so on and so forth. What is a functor between categories? Well, of course, it maps an object in C to an object in D. Majid will explain it in details. But it also must map any morphism. If you have a morphism, say, from C1 to C2 in C, okay, and C1 is mapped to D1, and C2 is mapped to D2, then also a morphism, any morphism between C1 and C2 must be mapped into a morphism between D1 and D2. Okay? There are some, and it must preserve the composition. This is very important. If you have F of a composition of morphisms in, oh, this is quite a nightmare. I'm so happy I'm using the blackboard later on. So imagine that you have a morphism G, which goes from C1 to C2, and you have a morphism F, which goes from C2 to C3. You compose the morphisms, and of course, you get a morphism now which goes from C1 to C3. Okay? I'm skipping lots of details because Majid will do it. I just want to do sort of a bare minimum, and I assume many of you know it anyway. So this is a very important property. That this is just the composition of F with F of G if a functor is covariant, and if a functor is contravariant, the composition goes the other way around. Majid will explain all of it. Okay, but this is the crucial property. Okay. Right, and now I want to think about the graph as a small category. This is just a linguistic gadget. There's nothing deep inside it. It's just the language. Okay, because when you say a functor between categories, you already think about so many natural properties that you don't have to spell out, like this one, for instance, right? So what are my objects when I want to think about the graph as a category? My objects are vertices, of course, right? And what are my morphisms? My morphisms are finite paths. They have a vertex V and a vertex W, then any finite path starting, of course, if it's between two vertices, it must be finite. Any path starting at V and ending at W, I consider as a morphism from V to W. So the space of all paths from V to W is the space of all morphisms. It's the set of all morphisms from object V to object W. Okay? Well, because if I have a path which has a beginning and an end, right? Then I suppose. Maybe you're right. Maybe you're right. Maybe you're right. Maybe this is it really possible? Yeah, I guess yes. Okay, I can take it back. I want finite paths. Maybe indeed, if I just, it's hard for me to imagine an infinite path which has both the beginning and the end. Typically, when you have an infinite path, either it has no end, or it has no beginning, or it has neither. But now you are saying that it's an infinite path. No, I can imagine, you know, this, but I think one thing is to have a picture. Another thing is it really satisfying all axioms? I don't know. Because I define a path as a sequence, you see. I'm not sure you're right. Because I define a path as a sequence. Okay. So how would you give me an infinite sequence which would have an end, both the beginning and the end? If it has the end, it must have the last vertex, the last edge. If it has the last edge, then I don't see how it can be infinite. This was my problem. Convergent. Sure. Yeah, I know, but you are changing the definition of the end of the path. I think that you might be right if we change the definition of what we mean by the end of a path. Right now, the end and the beginning of a path is defined in such a way that there is no end of an infinite, of a sequence which goes to infinity, because I'm saying take the last edge, but there's no last edge if you have infinitely many of them. But I know what you mean. You can modify the definition of taking an end so that it accommodates infinite paths. Yeah, I like the idea. Yeah. But formally, as I wrote it down before, if I have a beginning and an end, it is a finite path. But in any case, it's very nice. It's very good. We can alter the definition of a beginning and an end of a path by this convergence property, no problem. Okay. And then here we just assume, all right, a morphism is a finite path. Okay. So now, well, this is very important for you to remember, is that if I have F going, this commutative diagram is very crucial. If I have F going from C1 to C2, and I have capital F, my functor, going from C1 to D1, and of course also going from C2 to D2, right? Then by the definition of a functor, covariant functor, I also have a morphism F of F going from D1 to D2. Okay, this is the essence of being a functor. And it's contravariant if this arrow goes the other way around, then it's a contravariant functor. Okay. So in other words, when I say I have a functor between graphs, what do I mean? I mean that I have the usual old-fashioned set theoretical map from all finite paths in one graph to all finite paths in another graph, but it has a bunch of properties. To begin with, it sends vertices to vertices because a functor sends object to object. So I cannot send a vertex to a path, which is not a vertex, okay? So that's first part of saying that it's a map given by a functor. Secondly, if I send a finite path in one graph, the finite path in another graph, where endpoints must agree, exactly like in this commutative diagram. So if I have a vertex, if I have a finite path which starts in a vertex 1 and ends in a vertex 2, and I'm mapping it to a finite path which starts in a vertex D1 and ends in a vertex D2, then this vertex D1 must be the image of vertex C1, and the vertex D2 must be in the image of a vertex C2. Right? This is very important, is that these endpoints agree. I mean, start points and end points agree. Yeah. So if I send a finite path in one graph, the finite path in another graph, then of course I'm also sending all vertices in one graph to vertices in another graph, and I must have a commutative diagram like this. Okay. So when I say that I have a functor between graphs, I think about them as a small category. I think about finite paths as morphisms. I think about vertices as objects, and I have all these nice properties satisfied. And I don't have to spell them out in the theorem. All right. Which diagram? This diagram? Yeah, because f is not a function; it's a functor. Ah, small one. This is true for any morphisms from C1 to C2, and of course for any pair of objects C1 and C2. Yeah, there is always this for all quantifier. Yeah. It's covariant. Yeah, it's covariant because it preserves the direction of your morphism, and it's contravariant if it reverses it. Okay. And the funny thing is that here we have both. This is why I call it the wrong way morphism. Because so far I was going into the contravariant setup. One category is the category of graphs. Another category is a category of graphs, Easter algebras, or Levi path algebras. And if I have an inclusion of graphs, I include E into F, then my surjection goes from the functions on F, or given by F, to functions on E. This is contravariant. My star homomorphisms go the other way around than the inclusion. Just like in topology, if I include a closed set in a compact house of space, then my star homomorphism will be from functions on this big compact house of space onto the subspace by restriction. This is contravariant. I'm changing the direction, okay? But here, for this lemma, I will have the wrong way morphisms. I'll show you how from appropriate functor between graphs have star homomorphisms between graphs Easter algebras going in the same directions as this functor between graphs. And now I know it's already getting confusing because I'm calling a morphism between graphs a functor, but that's when I think about graphs as a small category. Okay. So I think I can kill it now and go back. Wait. So everybody sees it now, right? Slides. Yeah, or should I double check it? Where is my Zoom? Share screen. I don't know, I should check it. There's something in the chat, but I cannot answer chat. You could say, Alex, please, if you want to say something, say something. I cannot read your chat when lecturing. Just we can do it at the seminar, but at the lecture, just unmute yourself and speak, okay?
Yes. I just wanted to mention the results, like with Paresnikov, like about the pullback. Like it could be also viewed as like the pullback is a graph algebra again.
Yeah.
Which is not necessarily
sure, but I'm saying a bit more. I'm saying what exactly is this graph, and the whole point is that I'm trying to say that we are building a functor which turns push out into pullbacks, just as the graph functor does in classical topology. Okay.
My mean was like for example the extensions of graph algebras. You know, like these problems like the extensions of graph algebras not necessarily are graph algebras again.
Yeah.
And here in this case we have a positive answer to it.
Yeah, surely. Okay, so let me continue. How do I go back? Share, sorry. Okay, I'm still learning. Yeah, I guess everybody can see it on Zoom because I have a Zoom thingy in front of me. Okay. So when I say this fancy thing, let E and F be graphs, and I have a functor between graphs. All I mean is that I have a self-theoretical map from all finite paths on F to all finite paths on E, because paths of length 0 are my objects, and paths of length, well, actually, identity morphism is identified with an object. Okay, so that's the way it's done in the category theory. And calling this self-theoretical map a functor is done only so that I don't have to list the zillions of obvious properties that I want them to be satisfied, and which are automatically satisfied when you think about graphs as small categories, and when you think about these self-theoretical maps as morphisms. Okay. So in saying that F is a functor, I just have my self-theoretical map, which has a bunch of nice properties which I just explained. Okay. So first, we assume that F is injective on the set of objects. And you should already guess why. Well, I want to build this time a covariant functor. So at the end of the day, I want to have an induced map which goes in the same direction. You see, I have a map from F to E, and then I have a star homomorphism from C star F to C star E. This is covariant. Remember the theorem which we just had was contravariant. I have an inclusion from E to F, and I have a surjection from C star F to C star G. That's the other way around. That's contravariant. Okay. So why do I have to say that it's injective on morphisms? Well, look at this property in the definition of a graph C-star algebra. Whoops. These are mutual orthogonal projections. Okay. So this means that if I take two different vertices and multiply their projections, I must get 0, right? So imagine I'm non-injective on vertices. So there are two different vertices which are mapped to one vertex. And then I have two different projections which are mapped to one projection. And here it goes wrong, because PV times PW is 0, but then PV goes to PV prime, PW goes to PV prime, and PV prime times PV prime is PV prime, it's not 0. Later, we will have a basis theorem for Leavitt-Path algebras and graph C-star algebras which says that these generators are all linearly independent. The relations, these three relations, do not induce linear dependence between the generators. So as you know, elements of a basis are non-zero. Okay, so you have a contradiction. There's no map like this. So for starters, even before we begin anything serious, we must assume that F is injective on the set of objects, which means vertices. Okay. Now, I want to preserve this second Kunstkrieger relation, right? This relation, it would be so convenient if I could just click and go back to the right property, but I don't know how to do it. I know it's possible, but I'm not. You see, now I want to preserve this condition. So I want to have my morphism of C-star algebras, which is induced by this morphism of graphs. And for this to happen, I must make sure that this induced map will preserve all the relations, right? And now I'm worried about the second relation. And in order to make sure that this is satisfied, that this relation is not violated, I assume that for any regular vertex, which means one which emits at least one at the most finitely many edges, F restricts to a bijection, okay? So I have a regular vertex, it emits non-zero finitely many edges. I map this vertex to another vertex. It also emits some edges. And I'm saying that every edge, of course, every edge emitted at V must be mapped into an edge emitted at F of V. This is part of a definition of what I mean by a functor, or what I mean by a morphism between graphs. But now what I'm saying is that here this map from all finite paths in F to all finite paths in E, when restricted just to this set, must be bijective onto this set. And this is necessary in order to have a second relation in the definition of Graf-System algebra preserved. Because the finite sum is a finite sum, and it must be equal to a concrete projection. So I cannot change the number of elements in my sum. It wouldn't work. Yeah? So I must make sure here, or at least this is the first obvious guess. This is that condition. So these conditions are taken verbatim from a lemma, analogous lemma in Leavitt-Path algebras. Yeah? We are not being very creative here. And Alex, correct me if I'm wrong, but we are trying somehow to modify this condition, make it a bit more general, but yet guaranteeing the preservation of all Kunstkrieger properties in the definition of a graph.
Yes.
Yeah. So, but we are working on it. It's work in progress. You know, that's typical in mathematics. We want to have as few assumptions as possible with as big result as possible. Right? You want to pay the least amount of money for the best thing you buy. That's somehow also in economy. So right now we are paying a high price because this is a very restrictive assumption, but it works in many examples, and it immediately guarantees that the second Kunstkrieger relation is guaranteed. Because everything is just transported. We are just we take a certain equality that the sum of a finite set is equal to a projection, and we now relabel it. So it will be preserved. Yeah. But we must know that that f of v is also a regular vertex, and it emits exactly as many edges, and when projections agree because the functor, so it all works. And here's the fun part. This is, if you want, our addition. This is what you will not find in Leavitt-Path algebras book. That's what we did. So we want to assume they have a condition which is a very special case of this one. So now what we are doing, we are paying much lesser price for the same result. They paid $1 million, we are paying $100 for the same product. Okay? And this is our $100. What we assume is that f maps any two different edges to two paths such that no path is a prolongation of the other. Okay, so this is explicitly written like this. I take two different edges. Then f of e1 is a path, and f of e2 is a path. Okay, and it must not be the case that the path f of e1 is just the path of f of e2 plus some more edges. So f of e1 is not the prolongation of a path f of e2, and vice versa. F of e2 is not a prolongation of a path f of e1. Okay, so we demand
prolongation mean at the end of.
At the end, yes, yes.
It could have loops.
Yeah. Surely, okay. Surely. It's exactly as written here. You say that one path is a prolongation of the other if it is equal to this path and some more edges which are adjoined at the end of this smaller path. So you prolongate from end forward, not from the beginning backward.
Could you have some difference on the beginning?
Yeah, you could do it, but this wouldn't work for us. Because remember that the Kunstkrieger relations are not symmetric with respect to taking sources or targets. Okay, this is, if you go back again to this Graf-System algebra definition, look, this is very, very important. This is not symmetric. When we have this partial isometry property, it's concerned with the end of your edge, not the beginning. Now, when you want to look at the beginning of your edge, you have a far more complicated relation. That's not symmetric. And then this is also reflected of what we are doing, right? Endpoints and starting points play different role algebraically. Okay. By the way, I should also warn you that there are two competing conventions, and this is like half and half. It's half of mathematicians in the world believe that 0 is a natural number. The other half believes that 0 is not a natural number. In the United States, you always start from floor number 1. There is no ground floor. And in Europe, you always start from ground floor or floor 0. So there is no way to settle this conflict. Yeah? The same is the convention for graphs. There is a set of people who do it the way I do it, and this is how it all started. But there is also a significant set of people that they do it the other way around. So they interchange the concept of the source and the target. So everywhere in my definition, I wrote here the target, they would write the source. And here, when I write the source, they would write the target. But they also draw graphs the other way around. So when you look at our graphs and you want to obtain the graphs of the way other people do it, you have to reverse the directions of all arrows. This is extremely annoying, but we cannot help it. For instance, there's a there is a book, famous book by Ian Rayburn. By the way, so this book by Ian Rayburn was called Operator Algebras so that one can see. So I picked up this title, of course, from him. But then he changed it into a boring title, Graph-System Algebras. So there is a book by Ian Rayburn, it's the Bible of Graph-System Algebras, called Graph-System Algebras. And unfortunately, he switched from this convention, which was used to begin with, to the opposite convention. I mean, there is some reason for it in terms of going to higher rank graphs. And when you go to higher rank graphs, so if you want to add colors to the edges, then somehow it's more natural to have these directions reversed. But I prefer the old convention. But at least for this course, let me stick to the old convention. Okay, so these are our assumptions. This is the price that we pay. And what do we buy? Well, we buy a star homomorphism, right? Then F induces a star homomorphism from C star of F to C star of E, given in the most obvious way, functorial way, right? When I have my projection PV, so remember, I have, these are the universal C star algebras generated by projections and partial isometries. So if I define my star homomorphism on all generators and prove that the relations are satisfied, I'm done. I have a nice map between C star algebras. At a certain point, I hope Jacek will explain it to us in the recitation class, but not now. And so what do? I take my generator PV. So where do I send it? That's completely obvious. I take my vertex V, I send it to a vertex F of V, and to a vertex F of V, I associate a projection. And the same I do with partial isometries. I have my edge X, I send it to a path F of X, okay? And I associate to this generator Sx, I associated the following element, S of F of X. And now you can think, what is this? What is a partial isometry of a path? Well, this is something very obvious. Maybe I should have defined it earlier. It's something very obvious. When I have a partial isometry associated to a path, what I do, say, imagine the path is E1, E2 to En, okay? Finite paths, always finite paths. Then isometry associated to a path going from E1 to En is just S of E1 times S of E2 times S of E3, blah, 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 dot, 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 up to S of En. So that's by definition, the partial isometry associated to a path, okay? So yes, F of X is not an edge. Yes, F of X is a path. Okay, so in the Levitt book, this is just an edge, but for us it's a path. But it still works, and I can just say that this is the partial isometry given by all partial isometries. Okay, this is clear. If you do on a blackboard, I'll write it down, but switching back to this whiteboard will take far more time. Okay, so that's the upshot. Now this is what we call the wrong way morphisms, because somehow we would like to maintain this Gelfand picture of having a contravariant functor from the category of spaces, the category of C-star algebras. We'd like to have a contravariant functor from the category of graphs to the category of graph C-star algebras. Okay, but this beast is covariant, whether we like it or not. But I'll show you. Oops, my goodness, I should finish in 5 minutes. Oh no, it doesn't look good. So I'm afraid I'll break my word, and because I have to finish the slides today. So let me speak until I finish it, because I don't want to do it as the third time. Okay. Any questions about this theorem? So these are the two ending landmarks for the course. I want you to prove for you these two theorems, at least the first one. This one is more fancy, but I think it's within reach. Sorry, this is just a lemma with this. This is just a lemma. Now the theorem is here, right? So the first theorem, the easier one, is just about handling of injective pushouts. It's about handling of the union of graphs. Now I want to speak about pushouts of graphs which are not injective, because this is what happens in so many examples, okay? And I also want to have a pullback theorem, which tells me under which circumstances I can turn my pushout of graphs into pullback of sister algebras, okay? So here is getting complicated, but well, the proof is 1 page long. It's not such a horrible beast. So first, well, I have to show this diagram. I have 4 graphs, E1, E2, F1, and F2, okay? When I look at these 2 pairs, F1, E1, and F2, E2, I assume that F1 is admissible in E1, and I assume that F2 is admissible in E2. So I have these 2 canonical surjections, okay, by the theorem which I showed you earlier, okay? So this is the usual way, star homomorphism. But now here I have this induced beast from the lemma, okay? And in order to ensure that I do have these induced wrong-way morphisms from the lemma, I have some conditions. And I have more conditions because not only I want these maps to exist and make this diagram commutative, but I want this to be a pullback diagram. So I have to check Peterson's conditions for a pullback. So that's why there are so many assumptions. So here we pay still quite a price. So what do we assume? I assume that E1 has no loops. So this graph has no loops. And I also assume that when it comes to vertices, the graph E1 and E2 have just the same vertices. So the graphs E1 and E2 differ just by edges. This is the same set of vertices on both sides. Okay, the same goes for F1 and F2. So F1 and F2 are subgraphs in E1 and E2 respectively. But again, vertices in F2 are exactly vertices in F1. F1 and F2 differ only by edges. Okay. Now, E1 has no loops. So then, of course, also F1 has no loops. Now, E2, so I come here, has no length 1 loops at the vertices which are beyond F2. So I look at all vertices in E2 which are not in F2. Remember, F2 is a subgraph. And I do not allow that these vertices have a loop. Remember this ball and sphere? This is exactly what happens here. This is my subgraph. This is my graph. Okay? And in this vertex, which is outside of a subgraph, there is no loop. Here, there is no loop. So that's what I'm assuming in general. Yeah? When I look at vertices outside of a subgraph, then there must be no edges which are loops at these vertices. Okay? Yeah, so this is this assumption. E2 has no loops at vertices outside of F2. Now, as in the lemma, we have a functor from E1 to E2. And now we not only assume that this is injective, over there we just need it for the lemma for F to be injective on vertices. Well, we actually assume that it's identity on the vertices. I can say identity because I just assumed that the set of vertices in E1 and E2 is the same. So there's nothing happening on vertices, okay? And now I have this very important assumption that when I look at this map from finite paths in E1 to finite paths in E2, it is bijective when we restrict its codomain to the set of all pointed paths. Remember the definition of a pointed path? We had it earlier. A path is pointed, a finite path is pointed if its final edge is not a loop. Okay. So I take my graph E2, and I take not just all finite paths, I take all pointed paths. So I take all finite paths with a property that the last edge is not a loop. Okay? So when I restrict the target, the codomain of this functor f, of this map f, it is a bijection. Okay? That's an assumption. And we also have this assumption, which we made earlier, that any two different edges are mapped into paths such that one is not the prolongation of the other. This is this condition number 3, if I explain. Yeah, because we want to use the lemma, so we must somehow put the assumption inside. So we are in fact putting more assumption inside, because we need more than just the existence of these morphisms. We also want it to be a pullback diagram. That's why there are more assumptions. Okay? So once we paid 1 and 2, we buy the pullback diagram. Here, these maps are given by contravariant functors. I have admissible inclusion of F1 in E1. I have admissible inclusion of F2 in E2. And then here I have these wrong way morphisms, these covariant morphisms. I have induced map from C star of E1 to C star of E2. And you can check that it co-restricts, that it preserves the kernel. It co-restricts to a quotient map in here. And then you can check that the co-restriction of this map to that map, in fact, is the same as the map induced by the restriction between of a morphism from the graph E1 to the graph E2. You can restrict it to a morphism from the graph F1 to F2. And it also will satisfy all axioms of lemma 3, and it will induce the map. And this will agree with this co-restriction. Right, remember, because this is a surjection. So here's an ideal, okay? So when do I have, what does it mean to have a co-restriction? When I have a map from A to B, okay? And then I have a canonical quotient from A to A mod I and from B to B mod J. When can I say that F from A to B co-restricts to a map from A mod A to B mod J? Well, obviously, if a map F will map the ideal I into an ideal J, then it's well defined on the quotient, right? Because I go to the quotient space A mod I take an equivalence class of A, I lift it to A, I map it by F to B, and I go down to B mod J. And this doesn't depend on the choice because of this inclusion property. This is the co-restriction property. Yeah. And you can easily check that this works because you have a theorem about how the ideal looks like, and you see that this induced map maps the ideal, which is the kernel of this map, to the ideal, which is the kernel of that map. So you have a co-restriction. Okay. And the diagram is automatically commutative. What you have to work on is to prove that it's a pullback diagram, and this is one page of a proof. And that's as far as we can get, I suppose, in the course, if here at all. And all that remains are examples. So I'm any questions here? Because I'm done. This is where I want us to come during the course, if possible. We'll try it. I don't want to rush it. I prefer to say less, but in a comprehensible manner than too much in an incomprehensible manner. That's sort of the goal. But if we don't climb Mount Everest, at least we'll go to Lhotse. So any questions thus far? Because now it's examples and we are done. Any Zoom people? Okay. So examples.
I don't know if it's only my problem, but I have problem with sound.
Me too.
I don't hear anything too.
Me too. Like from everybody in class.
A teraz mnie słychać? Tak. Słyszycie mnie?
Tak.
Teraz bardzo dobrze.
Tak, tak.
Super. No tak, oczywiście to się mogło stać. Well, what happened was a battery on the receiving end. You see, this is like a walkie-talkie. I have one gadget, and there is another gadget which receives the signal, and we have to just change the batteries. Time up to a single second. They're supposed to end 7 minutes ago. That's why the battery went dead. Okay. You see how precise is our IT team at the IMPAN? I said that I should finish at 13:30. So the battery went down at 13:30. Can you hear me now?
Yes, yes.
Excellent. Sorry about it. Okay. So this is was a motivating example for the theorem which I just showed you. Because the Podley sphere sister algebra is something very famous, very well known and studied. There are really hundreds of research papers about the Podley sphere. And if you look at it as a sister algebra, it's something very simple, the minimal unitization of compact operators. But it follows this idea from topology that what you do, you take the unit disk and you shrink a circle to a point, okay? For those of you who know, which is probably just Jacek, you can take the Teplitz algebra as a quantum disk. I'm sure you know what it is because I just gave a talk about it. And then if you shrink the boundary circle to a point, you get precisely the Podley sphere. And you get a pullback diagram like this. This is well known. In some papers of Masuda and others, they wrote exact sequences for SUQ2 sister algebra, which were equivariant. So they would restrict to the fixed point sister subalgebras involving Podley sphere. And then you would get the short exact sequence, which can be equally well written as such a pullback diagram. Okay, so that's what we are having. The sister algebra of a graph which has just one loop. This is the continuous function in a circle. Okay, of course, if your graph is just one point, one vertex, no edges, this very complicated graph sister algebra definition will give you just complex numbers. More generally, if you have no edges, right? If you have no edges, all that you'll get will be functions on vertices. Okay, these are the edges that introduce the non-commutativity. If you want quantum interactions between classical objects. I'm kidding. I don't know. It just looks like it. Mathematicians like this physics sauce to spice it up. But here, this is the Teplitz algebra from Jacek's talk on Wednesday. Yeah, the graph sister algebra of this graph is the Teplitz algebra. So if you want to think about it as the continuous functions on the quantum disk. So now I look, and this is exactly what you saw with balls. Remember, disk is after all a two ball, and the circle is after all a one sphere. So what we already discussed at length, this is the lowest dimensional case. And this is a very famous map in index theory and so on, the symbol map from the Teplitz algebra to the circle algebra. This is like in zillions of books and papers. This induced map is a very famous one, but now interpreted in a graphy way and have a higher dimensional version. Okay. So this is like a disk with a boundary circle, which I shrink to a point, and I get the sphere. All right. But now I want to do it in terms of graphs. Okay. So first, I want to have these canonical quotient maps. Well, and you can verify that if you kill this vertex, if you look at this vertex here, well, let me put it this way. This edge, this vertex viewed as the beginning vertex here is an admissible subgraph. It satisfies all the conditions. So this means that this one-point set is saturated and hereditary, and this is not the breaking vertex. Yeah, this is not the breaking vertex because it shoots all arrows outside. if this was shooting some arrows, if you would attach a loop here or something, it wouldn't work. Yeah. But the point in this graph with countably infinitely many edges going from the first vertex to the second one, from the left one to the right one, that's an admissible subgraph. Also here, this is what we discussed. We discussed it with spheres in balls, so this is in particular circle in the disk. So this is also admissible. So here we have this canonical surjections, okay? This is just a character. The Podley sister algebra has one character, and this character will map here to complex numbers, okay? And this is the famous symbol map from index theory. You map a Teplitz operator to its symbol. You go from the Teplitz algebra, the quantum disk sister algebra, to functions in a circle. Okay. That's the second canonical quotient maps. So this is well known. Now what we have to do is cook up these maps. And here how we got this idea that we must map edges into paths. So you see, here we have infinitely many edges, here we have finitely many edges. But if you look at them as paths, at this diagram on the right-hand side, you also have infinitely many paths. Because I can go from the left to the right just by one edge. I can go around the loop and then go right. I can go around the loop twice and go right. So I have countably infinitely many paths from left to right. Just like here, I have countably infinitely many edges from left to right. So you can guess what I'm going to do. I map the first edge in here into this edge in here. I map the second edge in here into the loop followed by this edge. The third one into two loops followed by this edge, and so on and so forth. This will be my map. And this will be precisely this wrong way morphism. It will give me this wrong way morphism. It will satisfy the assumptions of lemma 3, and it will induce a map, which is a map from the Podley sphere sister algebra to the Teplitz algebra. Okay? You have this map. And then if you restrict it to the subgraph, then you go from the sister algebra of the subgraph to the sister algebra of the other subgraph. But here, this is obvious. This is just the unit map. I'm mapping the algebra of complex numbers into the algebra of functions in a circle. There's only one way to do it, the unit map. I'm mapping a number into 1 times this number. This is a star homomorphism, okay? So this map is completely obvious. So this is a character, and this is the unit map. And because we knew for 30 years that such a diagram exists, well, we were asking a question, can we do it in more generality? Does this idea of mapping edges into finite paths can work? In what level of generality? Well, this is answered by our theorem, okay? But let's do more examples. This is our motivating example. This is how we started the whole story. But remember, I told you that also if you take quantum real projective space and shrink an appropriate circle at a point, you also get a sphere. We had such an example at the beginning of the previous lecture, okay? So here it's the same. This is the graph sister algebra of a real projective space. That's from my PhD thesis, not Podley this time. That's sister algebra. And the same works. And here just have a different distribution. Remember, it's not a difficult thing to set a bijection between one countable infinite set and another countable infinite set. Any way you want it, it works. Okay. So this will also give this is a push-out which will also give me a pullback of sister algebras. You have a Podley sphere, here have one, here have a circle algebra, and here have a sister algebra of quantum real projective space, RP2 plane, yeah, RP2Q. Okay. And now here's something which I call the quantum bonus. So people who work on Leavitt path algebras should wake up. Anya, you are there, I hope. So if you look, this is a story which I like to say. So of course, it was not Leavitt who invented Leavitt path algebras. Leavitt was a guy who in the 60s posed the following problem. If you have a non-commutative ring, it's not always true that a free module of a non-commutative ring has a dimension. So every vector space has a dimension, but it's not true that every free module has a dimension. In other words, what might happen is that you take your ring R, and you raise it to nth power, then it's a free module, okay? But you can take the same ring R and raise it to a different power, nth power, okay? And you have such rings where these two modules of different sizes are actually isomorphic. So Levitt asked himself the following question. What is a universal ring which has these properties? For instance, I have two natural numbers, n and m. Okay, of course, it's interesting when n is different from m. What is the universal ring which has this property that this ring to the power n is isomorphic as a module to the ring to the power m? And this is what he constructed. This is what Levitt did. But in fact, if you take one of these integers, one of these natural numbers to be 2 and another one to be 1, so in other words, you ask when your ring R is isomorphic as a module with its square. So when it's R isomorphic with R squared. Well, it turns out that it's exactly for the Levitt path algebra of this Hawaiian ring. Remember, in Hawaii, this is the kind of earrings people use. This Hawaiian earring, okay? And of course, you can do it with n. So if you would have n loops, then you would have Rn isomorphic as a module with R. So this is what Levitt did. And when at the level of sister algebras, it was done by Kuntz. That's why in graph sister algebras, this is called Kuntz algebra 02. And this is something purely quantum. This space has nothing. It doesn't have any characters, doesn't have any ideals, nothing. It's a big quantum blob. But it's absolutely fundamental in Elliott's classification problem of sister algebras. So that sister algebra is very, very important. So not only it was important in ring theory as constructed by Levitt, but it's also a very important classification of sister algebra. But it's something purely quantum. I cannot speak here any spheres. There's no topological algebra. This is purely quantum. This is operator algebra, which is as far removed from the classical space intuition as it can be. But we have a graph, a very simple graph, okay? For instance, this sister algebra has a funny property that its tensor square is equal to itself. It's very weird, but it's true. Yeah. And we can do some algebraic topology like math with this, even though this is a purely quantum thing. And the reason why I like it so much is that typically in non-commutative topology, what you do, you consider some sister algebras that have some characters. The characters give you like the classical subspace of the quantum space, and the kind of surgery, the non-commutative topology that you're doing is over this classical subspace. This is not very satisfactory because it's kind of doing some very restricted classical topology, and then you are blowing it up with quantum spaces, attaching them later on. But here, this is not the case. I'm doing my surgery over something completely quantum. I'm doing my trick of collapsing things to a point. I have a big quantum space and I collapse it to a point. That's really non-commutative topology, okay? And we have the same effect. We have this purely quantum non-commutative sister algebra of Kuntz, 02. We can extend it in this Teplitz way. And then again, everything is satisfied. This Kuntz or Levitt graph is an admissible subgraph in this graph. This we already had before, and lo and behold, I have this very, very non-commutative sister algebra, and I shrink now this big quantum space to a point, and again, I recover a sphere. But this is a quantum bonus. This has absolutely no meaning, classic, okay? But still, I have a pullback of sister algebras. Remember this example of two kissing spheres? So if you want, if you take the diagram, which is a loop and going to the left, think about it as one quantum disk. If you take the same loop and going to the right, this is another quantum disk. So this diagram is having two quantum disks glued together over the boundary circle. So this is a two-sphere. It's again the Podlesh quantum sphere, but so-called equatorial one. That is different from the standard one, okay? And now remember, when you shrink the equator of a sphere to a point, what will you get? Two kissing spheres. And this is the same what happens here, right? I shrink this loop to a point, and the price I have to pay, but now I have countably infinitely many edges going to the left, and countably infinitely many edges going to the right. And the picture is that I have two Podlesh quantum spheres, And standard quantum spheres, they have just one classical point, and I glue them over as one classical point. So that's another example of application of this theorem. Now, so that you don't think that I have to shrink everything to a point, you remember the CW complex a picture of complex projective spaces? Now we are doing this in the quantum world. Let me go back to it to make sure we are on the same page. See, so that's the podless sphere stuff. This is the quantum RP2 stuff. These are the kissing spheres. I have quantized all of them. And now I do the same with this one, right? I can do it in any dimension, but drawing general graphs in any dimension is too clumsy, it's too awkward. So I just took n equals 2, yeah? But here I have non-commutative deformations of these spaces, which are given by graph sister algebras. And again, I have a pullback diagram. So first I have a push-out diagram of graphs, and then by the theorem gives me the pullback diagram of graph sister algebras. Yeah, so it works in any dimension. Here, this is CP1, CP2. This is S5, and this is S3. Sorry, this is S3, and this is a 4-dimensional ball. Yeah. So I attach 4-dimensional cell to a 2-dimensional projective space to get a 4-dimensional projective space. So drawing CP1 to CP2. And again, the theorem works because this graph is admissible subgraph here. You put this as the first one over here. This graph is an admissible subgraph over here. We already looked at it because we have it in any dimension, right? And then again, the recipe is pretty obvious. I have an edge going from here to there, and I map it to a finite path going from here to there. Here I have countably many paths from here to there. Here I have countably many edges from here to there. It gives you a map F. It satisfies the assumption of the theorem. We have a pullback diagram of sister algebras. Okay, and this is already a non-trivial result. This example, this pullback diagram was not known before, because the previous ones, well, that's these are easy. Well, doesn't matter known or not known. This is easy, but this done in arbitrary dimension, that's a result. It's not so easy to prove that in any dimension this is a pullback diagram of sister algebras. And first, we proved it in a completely different way. Completely different way. This is an alternative proof that this is a pullback diagram of sister algebras because these arrows will simply give me, there is one thing where you should stop me, you see. There was a reason why I was telling you about wrong way morphisms, you see, because here I have my morphism going from F to E. So I cheated you here, right? I should have my morphism of graphs going this way. But then I would be screwed. What kind of a push out it is when directions of arrows are confused. Okay. Now here's the deal, and this is what we are working on to make it nice. Remember this assumption in the theorem that F must be a bijection onto the set of all pointed paths. A bijection can be inverted. So basically, when I write such an arrow, what I mean is the following. I take all pointed paths in this graph, and then I invert the bijection and I map it upward. Okay. So simply, I do nothing with a path here which is not pointed. Well, if you want, you can think about it this way, but you should define no finite paths. Well, then I can say the following. Every pointed path can be canonically projected onto a pointed path. Why? Because if it's not pointed, it has a loop edge at the end. So shrink it to a point. If you can have a loop, shrink it to a point, but the finite path, at a certain moment, you'll have no loops. Okay? So there is a canonical projection of any path, any finite path into a pointed path. So do this projection and then invert the bijection. And this is why I'm drawing this arrow in this direction. And then my functor is contravariant as I want. But that's very icy, right? This is very slippery. we would like to clarify it. But this is front line of research. I mean, we are struggling with ourselves, right? Maybe you can help us. I can formalize it. I can have a theorem and a theorem such as example, but I want to understand of how it works. I would like to construct really this Levitt category of graphs, where morphism would be such that I would have always a contravariant function. But that's not so easy because the natural map between graphs here is going from up to down. I map an edge to a finite path. This is an obvious map. The mapping edges from here to passing there, it's not so obvious. I have to invert the bijection. But I just gave you a recipe how to do it so that I can somehow make sense out of these errors, okay? And now really the bonus, the last two slides go beyond. So this is something which I want us to cover at the lecture course, recitation classes, whatever. Yeah. Now this is definitely beyond this course. But as I was telling you about K-theory of why people study graph sister algebras, because then you can solve many problems related to K-theory for these sister algebras once you have a graph presentation. This is really been given to you on a plate and not just homological algebra, not just abstract groups, but also generators, which hide some nice topology geometry inside. So I told you about K-theory, even though I'm definitely not covering K-theory in this course, maybe later on in another semester. So here you can also go from graphs to higher rank graphs. And roughly speaking, higher rank graph is like the usual graph, but now your edges have colors. So a graph of rank K is a graph where you have K colors. And then life gets far more complicated. But it works. You see, one of the caveats of graph sister algebras is that this is a class of sister algebras which is not closed, typically, not always, but typically, it's not closed under the tensor product. So a tensor product of a graph sister algebra, the tensor product of another graph sister algebra is in general, usually, typically, not a graph sister algebra. And that sucks because tensor product is very nice, okay? This is why you have these higher rank graphs, because if you have a graph sister algebra of rank K graph and a graph sister algebra of rank L graph, and you take the tensor product, then lo and behold, you get the graph sister algebra of a K plus L graph. And there is a natural idea of how to take the Cartesian product of graphs, colored graphs. So a Cartesian product of a K graph with an L graph will give you what? A K plus L graph. And you can make sense out of it. So there are many examples which are covered by colored graphs, by higher-rank graphs, which are not covered by the usual graphs. And this is here where research is almost nowhere. I mean, we have very few results for higher-rank graphs. We do have them, but very few. So this is an area where you can really rise and shine. And I want you to, as always, I want somehow to motivate it by a concrete example. So you see, this diagram showing you CW complex structure of projective spaces where you would include CPN minus 1 in CPN and have a nice push-out diagram. Well, you can do it one floor higher. Remember that projective spaces are just base spaces of the quotient maps. I mean, you have a sphere with a diagonal action of a circle, you divide it by this action and you have a projective space, okay? But you have such a diagram also at this level. So if you include 2n minus 1 sphere as the equator of 2n plus 1 sphere, so first you go to the equator of 2n plus 1 sphere is a 2n sphere, but then the equator within the equator is 2n minus 1 sphere, okay? So this is the standard inclusion. And of course, such an inclusion is U1 equivariant. So if you divide it by the action of U1, you'll have the inclusion of CPN minus 1 in CPN, okay? Now here what you've got, this is just the action map. So the circle acting on the sphere is mapped onto the sphere. That's just the action map. S2n minus 1 is included as the boundary of the ball 2n. And S1 is mapped to S1 by the identity, okay? Now we can extend this action map from the sphere to the ball. This is a nice exercise. We'll do it at one moment. So that's something nice for Niklas. He's an algebraic topology. He can write the formula here, right? And you can check when indeed this is a push-out diagram. Moreover, it is equivariant, where equivariance for these spaces with a circle means that you do identity on these spaces on the left and you multiply in the circle on the right. Then this is a push-out diagram of continuous U1 equivariant maps. So of course, you can go to the quotient and have a push-out diagram of the quotient spaces. And then here you'll have CPN minus 1, CPN. You'll have the sphere and the ball. Because it's obvious when I have something cross a circle and I collapse the circle, I just get something. Yeah. So here dividing by the action of S1 will just give you the ball and the sphere respectively. But here you'll get CPNs. And this is how you recover the previous diagram. Well, in particular, we have this very nice picture in low dimension. So I put S1 into S3. Think about it as the circle subgroup of SU2, right? And here I have a torus multiplication, group multiplication on the circle. And I view the left circle as the boundary of a disk. And then I map the circle to that circle. This is, if you want, a very special case of a Hajac splitting. Please forgive me my Danish. Hajac splitting of a free sphere. Normally, you would look at a free sphere as a gluing of two solid tori. But you can also look at a free sphere as the solid torus with a boundary torus collapsed to a circle. That's exactly this picture. This is a solid torus. This is the boundary torus. And I collapse the boundary torus to a circle. And this way I get S3. Okay? Now, you can have it if you use higher rank graphs. The following is a well-known fact. If you take the sister algebra of the famous Born-Haber CQ2, you have this classical subgroup B1 inside. So this is this natural graph sister algebra surjection here. Okay. And then you have a pullback diagram of sister algebras, but look what happened here. Here I must take the tensor product of graph sister algebras. And this animal is no longer a graph sister algebra, but it is a rank 2 graph sister algebra. So if I allow colors, okay, if I have this circle as yellow and this circle as red and put them together and take a 2 graph sister algebra, this will be the classical torus. And the same here. If I appropriately attach it, I will have a quantum solid torus, but I need 2 colors. I need another color for the left and a color for the right. So then look what happens. I have a push out of colored graphs, which will restore for me a very well known and useful pullback diagram in sister algebras. Okay. So if you remember, I was telling you about the certain short exact sequence, which people use to compute K-theory. And in fact, with very little tweaking, you can change the short exact sequence of sister algebras into this pullback diagram of sister algebra. So this is very well known. I'm just taking the building blocks in very well known stuff and phrasing them in terms of graph sister algebras. And what I'm preaching here is that this idea of having push-out diagrams can also cover these examples, provided that we allowed colored graphs, or if you want higher rank graphs. Okay. But this is completely for the future. I know basically one paper where some research is done using colored graphs. It's basically about gluing colored graphs. Under some very strong assumptions, we can also take the union of colored graphs and have a pullback theorem. Yeah. So that much is known, but not much more. I'm pointing you possibly, since so many of you are PhD students, I don't just want to teach you technology. Of course, I also want to do it. Yeah? I must do it. But I also want you to see some possibilities for doing research. So I'm sorry if I was a bit chaotic. I'm sorry if I was too fast. I'm sorry if I was not comprehensible enough, but I think it's very important that you see where the state of the art is, what can be done, what is not known also, all right? And I think that this is a perfect time to make a break. So let's resume 20 past 2, okay? Thank you so much.